Okay, good morning. We are down the home stretch, coming up to the end of the quarter. So we have plenty of time left. But one major topic and one major chapter left is AC power. After that is all going to be review, practice problems, going back to the beginning of the material, and then doing in class activities. Okay, so let's begin. AC power. And the reason I label it as 5.5 is because the book that we use, it's not a separate chapter, but it's part of chapter 5, going from AC analysis. Okay, so this is going to translate a little bit, not translate, but tie to the resonant circuits that we just saw. Okay, so let's begin with the qualitative explanation. Electrical power is transmitted over very long distances. As you might see in this image over here, you would have, at some point, you would have noticed these kind of long distance transmission lines. In fact, actually, if you go, let's see, where did I first see one here? Madonna Plaza, outside of Sprouts, park in the parking lot. I was parking my car like a few years ago. And then, I parked it, got out of the car, and I noticed, what is this huge structure right in the middle? And I looked up, and then I realized there's a pole transmission tower going right through the parking lot. Okay. And if you go north, you see transmission lines carrying those electrical power over the Cuesta Grade, Cuesta Pass, across the mountains. So it's transmitted over long distances. It flows from the utility companies to the consumers. Consumers are of two kinds, industrial and residential. This matters because most industrial customers have inductive loads because they're running electric machines, sometimes non-stop, 24 hours a day, 7 days a week, okay, depending on the environment. Residential usage, very minimal. The biggest appliances in a residence would be your washer and dryers, which have big inductive loads, right? Which have big inductive loads. So washers and dryers, you might run what? Maybe once a week, twice a week, right? So industrial customers pretty much have inductive loads that run 24/7. Residential customers, not so much. Biggest appliances with an inductive load would be like a washer or a dryer. And your HVAC unit, right? Heating and cooling. Heating and cooling is, of course, might be run more often, obviously, but washers and dryers, not so much. And why does it matter? Well, the inductive loads, when I say inductive, means it is dealing with an inductor, right? Electrically speaking, an inductive load is an inductor. Inductors and capacitors have reactance, right? Reactance is not a figment of anybody's imagination. Again, repeating the obvious. It is represented mathematically by an imaginary number, but it has a physical basis in real life, right? The reactance has to do with the stored energy in the fields, the magnetic field and the electric field. So the current and the voltages that is used to store the energy in these fields also have associated power. This power is associated with the reactance, hence it is known as reactive power. And so what we're going to study in this chapter are equations and relationships between reactive power, real power, and the total complex power. Okay. So reactive power is only associated with reactance. Reactance is associated with stored energy, and stored energy is only possible in inductors and capacitors, not in resistors. Okay. So the power associated with a resistor is termed as real power or average power. Okay, real or average power. And the power associated with inductor and capacitor is reactive power. When you have loads, meaning in residential or commercial, you have both real and reactive. And so the real power, the total power, real plus reactive. I typically don't like to use the word real, but that's what our book and homework problems use. Let's go ahead and use average. Real somehow implies that the reactive power is imaginary. But the real and imaginary, again, it's a mathematical representation. That's why we call it real power. So let's stick with average. So average plus reactive power gives you total complex power. Okay, total complex power. So far, so good. Now, the reason why this is important is because energy storage devices, when you apply AC, the energy flows in and out of these devices constantly, goes back and forth. Meaning if you have a source and you have a inductive load and a capacitive load, right? Inductive load and a capacitive load, the energy is continuously flowing in and out of the inductor and the capacitor. Energy is constantly being exchanged. Depending on the frequency, that energy exchange is fast or slow, right? So right now, this is a very simple illustration. Your source is very close to the inductor and the capacitor. But long distance transmission lines, when the power comes from the utility company, it's traveling like miles, sometimes hundreds of miles away. So when you're transmitting power over long distances, the energy exchange is also taking place all along that long distance. So this could be hundreds of miles, right? Hundreds of miles. So the energy that is coming from the utility company, and here you have inductive load, the energy is traveling back and forth constantly over long distance transmission lines. Make sense? Right? Energy flows in and out of the inductor and capacitor. Now, when your source is close to the load, that is fine. It's not that much of a problem. If you're building a circuit on your lab bench, it's all right. Not much energy is wasted. But when it's being transmitted over long distances, there is a lot of energy that is going back and forth needlessly. Okay. The energy that is being transmitted, we can separate out into two components. The energy that is required to perform the mechanical work, which is the real power, and the energy that is associated with the reactance, which is reactive power. Okay. They are not two separate things. When the utility company sends a voltage or current, it sends like a entire amount that is required to get your electric machine started up and going. Depending on the design of the machine and the values of the components, some portion, like maybe 50% is used for real, 50% is used for reactive, perhaps. Okay, it's all transmitted as one piece. Make sense? Right? So this energy transfer, where the real power is doing the actual mechanical work, but the reactive power, meaning the power associated with the reactance, is not doing any real work except setting up the magnetic field in that inductive load. Is transmitted back and forth over long distances. The more it travels over long distances, if travel increases, the losses in the line increase. And that is a big concern. Remember back to chapter 1 in one of the labs in the middle where I explained resistance of a conductor is directly proportional to the length and inversely proportional to the cross-section area of the conductor. Now, if your conductor is hundreds of miles long, the resistance of that wire, a short piece, maybe like a foot or 10 feet, might be like a few ohms. But when you increase the length to hundreds of miles, it has significant resistance. It causes significant power loss. Okay, so transmission lines, long distance transmission lines will cause significant power loss. That is also one of the reasons why we transmit at high voltages and low currents, because current results in a I square R power loss. Again, it's like a lot of equations and a lot of things tied together, okay? But the gist of it is, the more you send power over long distance transmission lines, the more energy you lose during transmission, okay? And again, the word I use is needless, okay? The reactive power is being transmitted needlessly. You transmit it once, it sets up the magnetic field. After that, there is no need for it to return all the way back to the utility company, because it's a needless power loss in that scenario. Now, let's take a pause and think over all of that. Let me know if you have questions. Any questions? Okay. All right. So established that we don't want the energy to be transmitted back and forth over long distance transmission lines. So how do we prevent that? Well, fortunately, we do have a component that is very similar to the inductor, but behaves in exactly the opposite way in some respects, and that is the capacitor. When you have a capacitor and you place it in front of your inductive load, it absorbs the energy that comes out of the inductor, and instead of traveling all the way back to the utility company, that energy now gets stored in the capacitor. Okay, so imagine this scenario. You have an inductive load, switch is flipped for the first time, and the inductive load requires some power. That power is real plus reactive. This is sent by the utility company the first time, meaning the first half cycle. Okay, the first half cycle, the energy flows into the inductor. So positive half cycle, energy flows into the inductor. Negative half cycle, the energy flows out, meaning negative half cycle, but instead of traveling all the way back to the source, we now place a capacitor in front. So capacitor absorbs the stored inductive energy. Remember, capacitor is opposite. So for a capacitor, the energy flows in the capacitor during the negative half cycle. And the positive half cycle, the energy flows out. So what happens? Any guesses? And I said this during our labs, also during the lab 7 and during chapter 6, resonant circuits. When you first flip the switch on, inductor receives the energy, positive half cycle, negative half cycle, it flows out. But instead of going all the way hundreds of miles to the utility company where the source is located, it flows into the capacitor that is connected right in front. And the capacitor absorbs it in the negative half cycle. When the next positive half cycle, the inductor requires the energy, it comes from the capacitor and not from the utility company. As the energy is now localized. Okay, the energy is now bouncing back and forth locally at the industrial customer's facility and not traveling back and forth over long distances. Okay, capacitor absorbs the stored energy in the negative half cycle. And C sends it back to L in the next positive half cycle. It bounces between the inductor and the capacitor. Like a ping pong ball or a tennis ball. Okay. So the utility company does not have to send that reactive power again and again and again. So you have accomplished two things. You have lowered the costs associated with sending the reactive power. Second is you are preventing power loss that occurs every time the energy goes back and forth. Okay. And remember, even at a low 60 hertz transmission frequency, that's 60 cycles in 1 second, meaning in 1 second, that energy would travel back and forth 60 times. So imagine if it's like on for 24 hours a day, how much energy is being lost. So two things are being accomplished. One is you don't have to send that reactive power every single time. The second is, of course, you're reducing the power loss that occurs. Okay. The design, not design, but choosing the value of the capacitor and designing that circuit is a whole different niche area in electrical engineering. But what you are going to do, which is something you already did in lab 7, if you're taking the lab, is basically power factor correction. Okay, power factor correction. So this is a new term. It's a very important term in power systems. Okay. Designing the system, choosing a value of the capacitor is known as power factor correction. This is also the topic of lab 8. Okay, lab 8. Basically, you choose a capacitor value such that the energy required by the inductor is now provided by the capacitor. Okay. As an example, let's say the inductor requires like 10 units of energy. Okay. And you choose a capacitor randomly, it might only provide 5 units. You want a capacitor that will apply 10 units, right? So that it's exactly balanced out. So the energy from the inductor goes into the capacitor and then flows back out into that inductor. Yes. So then, if the capacitor, well, that's a good question. The question being asked is, the explanation I provided is kind of like a simplistic example, right? If it requires 10 units and you provide, the capacitor provides like 5 units, that's not enough. We want to get it up to 10, which that's an ideal situation, which never occurs in real life. So the question being asked is, what if we provide more than that? Well, then the capacitor becomes a load, right? The capacitor also is a load. So capacitor does not have any energy of its own. So it's a very good question. Instead of providing 10, how about if we provide 11 units of energy? Well, that one extra unit has to come from the source. So instead of the inductor, now the capacitor is pulling more energy from the source. So it still is going back and forth. So it's a fine line, and that's why I said designing such a system is a very niche expertise in electrical engineering. But that's a very good question because it illustrates the point on how difficult that could be, maintaining that. Yes. So the question being asked, let me see if I understand it correctly. Is it cheaper if the capacitor takes more energy first and then that's a good question. I never have thought about it. But from what I know, at least from the theory that we know of here, we never go up to 100%. They always design it to be below 100%. Yeah. Because the inductive loads, they vary depending on the time of the day, depending on, how many machines are up and running, because it's never constant. It's always fluctuating. Sometimes the speed might be different. The voltage requirements, the current requirements might be different. So they have to take all of that into account. Even if you have just a single machine, the amount of voltage and current that's required depends on the usage. And so we can never predict how much an inductive load would require. It will always be like an average, like, hey, over a 24-hour period, our inductive load requires, a certain amount of energy. And so let's design a system for that. Yeah. So good questions. But does everybody understand the basics of why we study this and, what we're doing? Going back to the last topic of chapter 6, resonant circuits, that is what happens. If the system is perfectly balanced out, you have a resistor, capacitor, and inductor in a circuit, there's always going to be a resistive load, right? There's always a portion of the load that's resistive. If the energy that is required by the inductor or the capacitor is perfectly balanced between the two, what happens? The energy is now just bouncing around back and forth between the two. They do not pull any energy from the source. All of the energy coming from the source goes to that resistor. That is at resonance. So at resonance, we looked at the mathematical equation where we said that the impedance of the inductor and the capacitor balance each other out, right? But physically, what is happening is that the energy that is coming from the source gets divided between the inductor, capacitor, and resistor. But at one particular frequency, that energy is confined between the inductor and the capacitor. So they don't pull any energy from the source. All of the energy goes to the resistor. So the output across the resistor goes to maximum. For any other value, either the inductor or the capacitor might pull some energy from the source. So the resistor will get less energy. Okay. But at one particular frequency, depending on the value of L and C, that energy is perfectly balanced, bounces back and forth between L and C, and then resistor output is maximum. So power factor correction, if it's 100% corrected, 100% power factor, then that would be like a resonant system, which in real life, it never happens. So let's take a pause. You think on all of that and let me know if you have any questions before we move on to the equations. Any questions? Okay, shall we take a look at equations then? So there's going to be a lot of equations and a lot of new units, but they all have a similar structure. We are talking about reactants. We are talking about reactive power and complex quantity. So we are still using complex numbers. Real power is still represented by P. So real or average power is still represented with the letter P, unit watts. W. Reactive power associated with the reactance is noted by the letter Q. I believe they just took the next alphabet after P. And then, of course, R is reserved for resistor, so to not confuse. All right, Q is the reactive power. The units for reactive power is different. It's VAR, which stands for volt ampere reactive. Remember, they do need that reactance, and the reactive power needs actual voltage and actual current. It's not separated. You send 10 units of current. At the other end, the resistive portion might use some portion of that current, and the reactive portion would use a little bit of that current. Okay. So again, there is voltage, there is current. Okay, everything is still present as usual. And then, as I said, since we use the imaginary number to represent the reactive power Q, we add it all up together. So P plus Q, and Q is represented with the imaginary number J. We come up with a new term called S. S is the total complex power. And the unit for total complex power is simply volt ampere. Okay, volt ampere. And because it has a real component and an imaginary component, we can represent the total complex power S as a right angle triangle. Okay, we can represent it as a right angle triangle, and we call that as a power triangle. Power triangle. So you have real power P, or average power P on the real axis. Okay. Average power P is on the real axis. Reactive power Q is on the imaginary axis. And then, of course, the hypotenuse that joins all of them together. So this is for an inductor. This is for a capacitor. So real. Okay. Again, at the beginning, I said capacitor behaves exactly the opposite of an inductor. Goes back to the impedance of a capacitor being negative with an angle of -90. Okay. Impedance of an inductor is +90. Impedance of a capacitor is -90. And so that allows us to balance out the energy requirements of an inductive load with a simple capacitor. So you have P, and this can be signified as PL, QL, and PC and QC. This can be theta L and theta C. It's a right angle triangle. So it's a right angle triangle similar to the impedance triangle, and the phasors, it's like any other vector. You can treat it as any other vector. You can use trigonometric identities to determine the relationship between the four quantities. Yes? Oh, real and imaginary axis. That's all I plotted. Yes. Mathematical representation. Okay. The axes labels that you see here, real and imaginary, just mathematical representation. Similar to what we did in chapter 5, the phasor notations, the impedance, all of them the same. So again, a right angle triangle, you get, if you have any of the two quantities, meaning if you have P and Q, you can find the hypotenuse and the phase angle. If you have the phase angle and the hypotenuse, you can find P and Q. And so that's where these equations come from. Okay. P is VRMS, VI times cosine theta, Q is VI times sine theta, which basically comes from here, right? Right angle triangle. Okay. So that's the first set of equations. If you wish to find P and Q, you can find it using the trigonometric identities. Now, obviously, this only applies for that specific component, not for the entire system. Meaning, if you're trying to find P and Q for an inductor, then you need the RMS values of the inductor voltage and the inductor current. Make sense? If you're trying to find the reactive power for a, Q is right here. This is only for a resistor because it's average power. This is for inductor and capacitor. Q is associated with inductor and capacitor. P is associated with resistor. So again, no matter which component you're dealing with, once you determine the equation that you wish to use, you need to find the voltage and current for that particular component. So this is one set of equations that you can use. Power angle theta is the same as the impedance angle because it's the difference between the voltage and the current. It's the same as the impedance angle. Which is the phase angle of Z. Impedance for the inductor or the impedance of the capacitor, right? Theta Z. Theta ZL and theta ZC. Because impedance is also the phase difference between the voltage and the current. Theta V minus theta I. So impedance angle and power angle are exactly the same. All right, other equations. And we introduced a new term. We talked about the power angle. The power angle, if you take the cosine of that angle, it is known or labeled as the power factor. Power factor. It basically illustrates how much energy is required by the consumer. Okay. Remember, the goal is, and I'll go back to this triangle right now. What is the goal? Our goal is that the reactive power required by the inductor should be as small as possible. Okay, this is from the point of view of the source. This is from the point of view of the source. The source wants to send as little Q as possible. We want that Q to be very small. We want that angle to be very small. We want that Q to be as close to zero as possible. Real life, of course, is not possible, but the goal is to have as small value for QL as possible. Okay, so this is where it's very important. Let's say your QL required this is your required QL. And this is your P. Okay. If you place a capacitor that can supply 90% of this Q, then from that point end, it comes all the way down here, QC. And so the resulting triangle or the requirement is only this much. Does that make sense? Right? Your inductive requirement is, let's say, maybe 10 units. Your capacitor provides 9. So the source only has to send 1 unit after the first half cycle, of course. And that is, of course, known as the power factor correction. So we want that theta to be as small as possible, so that cosine is as high as possible. Okay. If the angle is 0, meaning no Q is required, which would happen at resonance, then its cos of 0 and your power factor is 1, unity. So ideal value of theta would be equal to 0. Cosine 0 would be equal to 1. And this power factor is typically stated in terms of percentage. So 1 would be the highest value, right? 0 is the maximum value. If the capacitor supplies more energy, now your angle goes negative, right? If you require only 10 and you provide 11, now you're going below the real axis. So then you have to send, I mean, it's a negative angle. The source still has to send energy. And so this is also labeled as percentage or 100%. I think typically, I think let's take PG&E for example. I don't know the latest numbers, but I think they require a power factor of at least 90%. Meaning cosine of theta should be 0.9, small angle. So in real terms, this is the consideration. When you first flip the switch on, it has to send all of that energy at least once, okay? After that first initial burst or the first initial reception of that energy, that inductive requirement should go down. Here's the critical thing. If you have 10 machines and you flip on all 10 all at the same time, let's say all 10 machines require like 10 units of energy. That means 10 times 10, you require 100 units of energy, right? So the transmission company, the utility company will say, we are not going to spend that much money to install the infrastructure to supply 100 units of energy all the time. We only have the capability to supply like maybe 40 or 50. Okay, so you first flip the switch on, you only turn on one machine at a time, staggered turn on. So you stagger turn on, first machine comes on, requires 10 units of energy, you send 10. After the 10, you only need 1. So only 1 unit is being sent from the utility company. The second machine is turned on, and the third and the fourth. So it's a staggered turn on. So when the power goes out in an industrial environment, the customer has to work with the utility company to actually get everything back up and running. So if you ever hear of blackouts on campus, it's a big deal because the campus has electric machines that run nonstop 24/7. The boilers in the central heating plant, where it heats up the water and sends it to every single room, every single building, those boilers are running nonstop. Okay, there are generators, transformers that run nonstop on campus. So if the power goes out on campus, they have to work with the utility company to bring it back on in a staggered manner. If you flip all the switches on at the same time, they're not going to send anything to you. They're going to say, you need to get your power factor back up before we send you anything. So the power factor has to be at a certain level before the utility company will send the customer any electric power. Okay, so it's a staggered turn on. All right, let's take a pause and let me know if you have any questions. It's a lot of new concepts. So hopefully, not hopefully, you'll have like, it's a 3-day long weekend. Hopefully you'll have some time, maybe half an hour, 45 minutes, an hour at least, to reflect back on everything. Yes. Breakers. Oh, circuit breakers. Yeah, if the current. Yeah. So the question being asked is about circuit breakers. So that is, yeah, that could be one of the applications. Yes. Circuit breakers essentially are if the current being pulled from the load goes too high, then it flips. Instead of fuse, we used to have fuses, but the fuses are like, every time it blows it out, you got to go and insert a new one. Circuit breakers, relays, it just trips. So it trips, then all you got to do is like, rectify your issue and then turn it back on. So yeah, absolutely. Current requirements. Okay, so let's look at the other. Oh, sorry. the other equations here. Cosine of theta, power factor, is also described as lagging or leading. The reference is the voltage, and we talk about the current, whether the current lags or leads. Okay, so if the current is lagging, so voltage is the reference, V is reference, and I is the measurement quantity. Okay, so if current is lagging, we say the system is lagging or the power factor is lagging. If I is leading, we say the system or the power factor is leading. Okay, and this happens only in an inductor and a capacitor. For an inductor, voltage always leads the current by 90 degrees. Remember, Eli the Iceman. Voltage always leads the current. If voltage is your reference, then you state that the current is lagging. So lagging only happens in an inductor, and leading, current always leads the voltage in a capacitor by 90 degrees. So again, voltage is the reference and the current is leading. So we say power factor is leading. So if the current lags, we say power factor is lagging. If the current leads, we say power factor is leading. Again, the point is, the goal is we want that Q to be as small as possible. So these quantities help us describe how the system is functioning. Okay, how the system is functioning. So from that right angle triangle, we can have a few more few more equations. And these again go back to Ohm's law and the power equation that we studied in chapter 1, right? The hypotenuse of the power triangle is the magnitude of S, right? You have P and Q. P and Q are the real and imaginary. So when you take the magnitude, if you take the magnitude of S is equal to P plus JQ, we define that as the product of the voltage and current RMS values, because that's the average value that's going in, right? So apparent power is the term that is given to the magnitude of S. Okay, apparent power is the term that is given to magnitude of S, and the units are still volt amperes. S, the unit for S, total complex power, is volt ampere. So magnitude of S is also volt ampere. Of course, S can be described as magnitude of S with the power angle theta. Again, right angle triangle. That's where it comes from. These equations come from combination of Ohm's law and the standard power equation. V equals IR and P equals IV. Chapter 1. If you'll remember, I stated this. This was again in the first week of class, so it's probably a distant memory. But chapter 1. So same standard form, no difference. Okay. Apparent power is the product of the voltage and current, but it's the RMS values, VRMS times IRMS. And then power, average power is associated with the resistor. So P is always associated with the resistor. Okay. P is not associated with L and Q. If it's L and C. If it's L and C, then the power is associated with the reactance X. Omega L, 2 pi FL. Reactance X or reactance XL for inductor is 2 pi FL. For capacitor is 1 over 2 pi FC. So again, QL is IL square times XL. QC similarly would be IL and of course RMS values times XL, and QC similarly would be IC RMS value square times XC. The form of the equation, the structure of the equation is exactly the same. I square times R. So Q is equal to I square times X. And everywhere we use RMS values, not peak values. Okay, not peak values. And one final equation is this. And of course, there are derivations for every single thing. If you're interested, stop by my office. I'd be more than happy to go over these in detail. But again, during the class, in class session, not so much time. It says half VI asterisk. The V and I are phasor forms of the voltage and current. The asterisk notes that is the complex conjugate of the quantity. Complex conjugate simply means this indicates it's the complex conjugate. And so complex conjugate simply means that A plus JB becomes A minus JB and vice versa. Or if it's R with an angle of theta, that becomes R with an angle of minus theta. The imaginary number is flipped around the real axis. That's what it means to be a complex conjugate. These are phasors. Okay. These are phasors. V and I are phasors. So they are complex numbers. V and I in that equation are both complex numbers. All right. 2 more slides, 2 more problems. We are not going to go into those today. We'll go into those on Monday. Well, one of the problems on Monday. So we'll end class here today. Please review this information while it's still fresh. 15 minutes, 20 minutes, and then take your time with it. That's the last homework in this class, homework 20. There's nothing more after that. I'll give you one more news is that we'll have the quiz on filters on Monday. That's quiz 8. And then quiz 9 in the last week would be on AC power. So it'll be AC analysis and AC power. But I will not ask AC power on the final exam. Tuesday, yes, sorry. That's a good point. Yes, Monday is a holiday. So we'll be meeting Tuesday and Wednesday. So quiz on Tuesday as normal because Tuesday follows a Monday schedule. So that'll be quiz 8. And the following week, the last week of classes, we will have quiz 9, which is AC power. And I will not ask AC power on the final exam. Okay, so we'll take our time in the next 2 weeks. All right. Wish you all a good, long, happy weekend. I plan to catch up on a lot of my grading work. Don't have any other life. That's what I'm going to plan to do. So take some time and relax if you can. I'll see you all on Tuesday.